In every place you go, there are power lines stretching across highways, fields, or city streets and more. Of course, you have seen them, but there should be something you've probably noticed. The long, gleaming cables connecting poles and towers in the sky. These wires carry thousands of volts of electricity across vast distances. And while most people might assume they're made of copper, the same reddish-brown metal found in household wires, they're not. The reality is, those high-voltage power lines overhead aren't copper at all. They're made of aluminum. And it might leave you wondering why. After all, copper is a better conductor, right? It carries electricity more efficiently. It's used in home wiring in electronic circuits and has long been considered the gold standard of electrical conductivity, second only to silver. So if copper is so superior, why is aluminum the metal of choice for power lines, where efficiency and performance really matter? Well, the answer has less to do with how electricity flows and more to do with the real-world challenges of weight, cost, and engineering practicality on a massive scale. Let's start with the basics. Yes, copper conducts electricity better than aluminum. In fact, copper has about 40% more conductivity than aluminum. That means, inch for inch, copper allows more electrical current to pass through it than aluminum does. So on paper, copper should win. But real-world engineering is rarely just about paper stats. When building power lines, which often stretch hundreds of kilometers across cities, countrysides, and deserts, engineers have to think about much more than just conductivity. One of the biggest concerns? Weight. Copper is nearly twice as heavy as aluminum. That means a copper cable of the same size weighs significantly more, putting tremendous stress on the towers and poles that support it. And when you're dealing with long spans between towers, gravity becomes a serious problem. The heavier the cable, the more it sags. That sag limits how far apart towers can be placed, increases material costs, and makes installation far more difficult. Using copper would require stronger, taller, and more expensive support structures across the entire grid. Over time, maintenance costs would skyrocket. Aluminum, on the other hand, is lightweight, less than half the density of copper. That means engineers can install longer spans between towers, use smaller support structures, and cover more distance with less material. Even though aluminum isn't as conductive, they can simply make the aluminum wire thicker to carry the same amount of electricity. And even after increasing the diameter, the cable is still lighter than a copper equivalent. Then there's the issue of cost, and this is where aluminum really pulls ahead. Aluminum is far cheaper than copper. In fact, depending on market conditions, aluminum can cost 3 to 5 times less than copper by weight. When you're talking about national power grids or long-distance transmission lines, where thousands of kilometers of cable are needed, this adds up fast. Even slightly cheaper material could save millions. But aluminum isn't just slightly cheaper, it's dramatically more affordable. And since power utilities work on massive budgets with tight margins, material costs matter a lot. But it's not just about buying the metal. Aluminum is also easier to process. It melts at a lower temperature, it's more abundant in the Earth's crust, and it's easier to extrude into wires and cables. That means lower manufacturing costs and simpler logistics when producing cables at industrial scale. Now you might wonder, if aluminum is so great for power lines, why not use it in homes? Well, it actually was used for home wiring, especially during the 1960s and 70s, when copper prices spiked. But in smaller applications like residential wiring, aluminum revealed one big weakness: connection stability. You see, aluminum expands and contracts more than copper when it heats up. Over time, this can loosen connections at outlets and switches, leading to overheating or even electrical fires. Copper holds tight and stable, which is exactly what you want in homes and small electronics, where safety is paramount and spacing is tight. That's why copper remains the standard in homes and devices. But aluminum thrives when it's in the open air, high up, and moving massive amounts of electricity across long distances. There's one more thing worth mentioning. Modern power lines often use something called ACSR, aluminum conductor steel reinforced cables. These are clever hybrid wires, where a steel core provides the strength and tension resistance, while the aluminum outer strands carry the current. This combo allows for lightweight, high-strength conductors that can stretch across valleys, deserts, and even mountains, safely and reliably. So what does all this mean? It means the decision to use aluminum instead of copper is all about balance. Aluminum may not win the conductivity race, but when you factor in weight, distance, cost, availability, and structural efficiency, it becomes the obvious winner for high-voltage transmission. In the air, across long distances, with towers spaced far apart, aluminum shines. It's light, it's cheap, and with a bit of engineering, it can perform just as well as copper where it counts most. That's why you don't see copper wires running through the sky, even though they might seem like the better choice at first glance. Sometimes, the best choice in engineering isn't the strongest, the fastest, or the most conductive. It's the one that works best in the real world. And aluminum checks all the boxes. So the next time you look up at those long, shimmering power lines above the highway, remember, they're not made of copper. They're a clever compromise, a perfect blend of science, strategy, and smart economics, all wrapped in the humble shine of aluminum. Thank you for watching. Please don't forget to like and subscribe. We have other videos for you. Please choose the left or the right video and subscribe.